In this video, we're going to look at the plate heat exchanger. By the end of the video, you will know all of the plate heat exchanger's main components, how it works, and some of the advantages and disadvantages associated with this type of heat exchanger compared to other types of heat exchanger, such as the shell and tube type. Plate heat exchangers consist of relatively few parts. Because plate heat exchangers are used for transferring heat, they require inlets and outlets where the flowing mediums, or fluids, can enter and leave the heat exchanger. A fluid may be a liquid or a gas. As fluids are often assumed to be liquid only, we will use the term flowing medium to avoid confusion. Gaskets and plates are used to separate the flowing mediums and prevent them mixing. The gaskets are adhered to one side of each plate only. The plates hang upon a carry bar and are pressed together using clamping bolts. When the plates are compressed together, they form a plate stack. A guide bar ensures the plates are aligned correctly when the plate stack is opened and closed. The final components of interest are two covers at opposite ends of the plate stack. One cover is movable, whilst the other is fixed. The movable cover and fixed cover are also sometimes referred to as the frame plate and pressure plate. Note that the inlets and outlets are mounted to the fixed cover only. Now we know about the plate heat exchanger's main components, let's have a look at how it works and some of its design features. For demonstration purposes, we will assume that we have two flowing mediums and that one is cold and the other is hot. The hot medium needs to be cooled by the cold medium, and this will occur in the plate heat exchanger. The hot medium enters the heat exchanger through the hot medium inlet. Gaskets direct the hot medium as it flows through the heat exchanger. Each plate has an alternating gasket pattern. The hot medium flows into the space between a pair of plates, but does not flow into the space between the next pair of plates because the gaskets prevent this. The process continues so that each second set of plates is filled with the hot flowing medium. At the same time, the cold medium enters the heat exchanger through the cold medium inlet, but this time the gaskets are positioned to allow the cold medium to flow into the space where no hot medium is present. We now have a heat exchanger that is filled with both hot and cold flowing mediums. Each medium flows out of its associated outlet and the process is continuous. Notice that the two flowing mediums are always adjacent to each other throughout the heat exchanger. The flowing mediums thus have a hot-cold flow pattern as they flow through the heat exchanger. They are completely separated from each other by the gaskets and plates, and they do not mix. Due to the close proximity of the flowing mediums, heat is exchanged between them. The hot medium heats up the plate, and the plate passes some of this heat to the cold flowing medium. Thus the hot medium temperature decreases, whilst the cold medium temperature increases. But what makes plate heat exchangers so efficient compared to other types of heat exchanger, such as the shell and tube type? Let's look into some of the plate heat exchangers' design features. The plates themselves are the main reason plate heat exchangers are so efficient. This plate may appear simple, but it is actually full of interesting engineering design features. For example, when the plates are compressed together to form a plate stack, the gap between each of the plates is very small, which ensures good thermal contact between the two flowing mediums. The gap between the plates is also known as clearance. Plates are thin and have a large contact surface area, which gives each plate a high heat transfer rate. Plates are manufactured from a material with high thermal conductivity, which further increases the heat transfer rate. Corrugations on the plate surfaces prevent laminar flow and promote turbulent flow, which increases the heat transfer rate whilst also reducing the likelihood of deposits accumulating upon the plate surfaces. The corrugations also serve to stiffen the plate structure, which allows a thinner plate to be used compared to a plate that has no corrugations. Note that plate corrugations are sometimes referred to as having a herringbone pattern. So although the plates look simple, a lot of engineering was applied to their design. But the plates are not the only part of a plate heat exchanger with extensive design features. Take the gaskets for example. The gaskets are able to maintain a seal between the plates even when the system pressure and temperature varies. Holes in each gasket, known as telltales, are used to identify leaking gaskets. This feature allows operators to change the affected plate before the leaking medium leaks through the next gasket and contaminates the other flowing medium. Because the gaskets guide flow through the heat exchanger, it is essential that they be installed in the correct order. For this reason, gaskets are often fitted with markings so that operators can check each plate is installed in the correct order throughout the entire plate stack. Another way to check the order of the plates is to spray paint a diagonal line from the top left to bottom right of the entire plate stack. Although we have only shown 2 gasket designs so far in this video, there are actually 3. Gaskets alternate throughout the heat exchanger except for the first and last plates within the plate stack, which press against the fixed and movable covers. Plates that press against the fixed and movable covers are known as start and end plates, because of their position within the plate stack. The purpose of the start and end plates is to prevent flow into the space between the fixed cover and start plate, and to prevent flow into the space between the movable cover and end plate. In this way, the covers are not actively used to exchange heat. This makes sense because each of the covers is quite thick, there are no corrugations, and they're poorly designed to exchange heat. There are several ways to vary the cooling capacity of a heat exchanger. One way is to regulate the outlet valves so that the flow is increased or decreased. This method is useful because no dismantling of the heat exchanger occurs. Another way is to increase or decrease the number of plates in the plate stack. Increasing the number of plates in the plate stack gives a corresponding increase in cooling capacity. Decreasing the number of plates in the plate stack gives a corresponding decrease in cooling capacity. In short, more plates equals more cooling, and less plates equals less cooling. The final method of varying a plate heat exchanger's cooling capacity is to use a single-pass or multi-pass design. Single-pass heat exchangers allow the 2 flowing mediums to flow past each other only once. Multi-pass heat exchangers allow the flowing mediums to flow past each other several times. Most plate heat exchangers use a single-pass design. Flow through a plate heat exchanger may be parallel, cross or counter. Plate heat exchangers usually use counter flow, as this is the most efficient type of flow for heat transfer. Counterflow is also sometimes known as contraflow. Because plate heat exchangers are used for wide-ranging applications, they must be designed to withstand the process conditions in which they operate. This may include corrosive and erosive environments. It's possible to construct plate heat exchangers from various materials, including metals, alloys, and plastics. Different materials make the plate heat exchanger more suitable for different applications. For example, if a particular flowing medium reacts aggressively when coming into contact with certain metals, polymer-based materials such as Teflon may be used instead. There are numerous advantages associated with plate heat exchangers. Plate heat exchangers weigh less, require less space, and are more efficient compared to other heat exchanger designs of the same size. Replacing and cleaning of the plates is a simple task, because the plate stack can be opened easily. And unlike shell and tube heat exchangers, plate heat exchangers do not require additional space for dismantling. But there are also some disadvantages. Plate heat exchangers tend to be more expensive than other heat exchanger designs. If there is a leaking gasket causing one flowing medium to mix with the other, the leaking plate is often difficult to locate. Replacement of plate gaskets in situ can be difficult or impossible. Some plate gaskets must be returned to the manufacturer for replacement, which costs both time and money. When plates are compressed together to form a plate stack, the clearances between the plates are small. This increases the likelihood of fouling with a corresponding reduction in the heat transfer rate. When reassembling the plate stack, over-tightening the clamping bolts can lead to crushing of the plates, which will damage the plate corrugations and squeeze out the gaskets. If the gaskets are squeezed out, the plates will no longer seal correctly. Plate heat exchangers are not suitable for high pressure applications because the gaskets would be expelled by the system pressure. This situation is referred to as gasket blowout. However, It is possible to get around this problem by using a gasketless design. These designs usually use brazed or welded plates. Brazed and welded plate heat exchangers are more suitable for higher temperature and higher pressure applications.